Atoms have electrons orbiting the nucleus in fixed shells or orbits. There is a definite amount of energy associated with each orbit or shell. The nearest orbit has the lowest and the farthest orbit has the highest energy. The closest shell or orbit to the nucleus is the K shell, second shell is the Al shell, third shell is the M shell, fourth shell is the N shell, and so on. The shells correspond to the principal quantum numbers, that is, n equals 1, 2, 3, 4, so on, or are labeled K, L, M, N, and so on. The figure shows the positively charged nucleus and electron orbits K, L, M, and N, with principal quantum number 1, 2, 3, 4 respectively. Each shell or orbit can hold a fixed number of electrons, given by the formula 2n square, where n is the principal quantum number. So, for n equals 1, that is, K shell can hold a maximum of 2 into 1 square equal to 2 electrons. For n equals 2, that is, L shell can hold a maximum of 2 into 2 square equal to 8 electrons. For n equals 3, that is, M shell can hold a maximum of 2 into 3 square equal to 18 electrons. For n equals 4, that is, N shell can hold a maximum of 2 into 4 square equal to 32 electrons. The figure shows the positively charged nucleus and a maximum of 2 electrons in the first or K shell, a maximum of 8 electrons in the second or L shell. Each shell or orbit consists of one or more subshells, S, P, D, F, and G subshells. The first K shell has one subshell 1s, the second L shell has two subshells 2s and 2p, the third M shell has three subshells 3s, 3p and 3d, the fourth N shell has four subshells 4s, 4p, 4d and 4f, the fifth O shell has five subshells 5s, 5p, 5d, 5f and 5g. 5. G subshell is not occupied in the stable state of any known elements. Each subshell is defined by an azimuthal quantum number L. L varies from 0 to n-1, where n is the principal quantum number. Each subshell can contain a maximum of 2 multiplied by 2, L plus 1 electrons. S subshell is in every shell, P in second and higher, D in third and higher, F in fourth and higher, and G in fifth and higher shells. The table shows the subshells S, P, D, F, G, their azimuthal quantum number L, 0, 1, 2, 3, 4, and maximum number of electrons in a subshell, 2, 6, 10, 14, 18. For example, 3D subshell has n equal to 3, L equal to n-1, equal to 3-1, equal to 2. Maximum number of electrons in 3D subshell equal to 2 multiplied by 2, L plus 1, equal to 2 multiplied by 2 into 2 plus 1 equal to 2 multiplied by 4 plus 1 equal to 2 multiplied by 5. Maximum number of electrons in 3D subshell equal to 10. The electron configuration is the distribution of electrons of an atom in different orbitals or shells. The electrons are filled in the various shells and subshells according to Madelung's rule, and Aufbau principle, which states that the lowest energy subshells are filled before electrons are filled in higher energy orbitals. Energy increases as n plus L increases, Madelung's rule. Subshells are filled in increasing order of n plus L. For subshells having same n plus L, they are filled in increasing order of n. The figure shows the order in which the electrons are filled in the subshells. Let's see the electron configuration of silicon Si. Atomic number of Si is 14, so the number of electrons is 14, which are distributed in the subshells as follows: 2 in 1s subshell, 2 in 2s subshell, 6 in 2p subshell, 2 in 3s subshell, 2 in 3p subshell. So the electron configuration of Si is 1s2, 2s2, 2p6, 3s2, 3p2. The same can be written in noble gas configuration, using the symbol of the last noble gas prior to Si, which is Ne, neon, followed by the configuration of the remaining electrons, so it will be Ne, 3s2, 3p2. The Aufbau principle works well for the known 118 elements, with very few exceptions where it is slightly wrong. Example: chromium Cr, atomic number 24. Aufbau's principle predicts an electron configuration, Ar, 4s2, 3d4, but actually, it is Ar, 4s1, 3d5. Another example is lanthanum La, atomic number 57. Aufbau's principle predicts an electron configuration, Xe, 6s2, 4f1, but actually, it is Xe, 6s2, 5d1. These happen due to many reasons. The half-filled subshells may be more stable, or the difference in energy between the s and d, or s and f subshells may not be much. An electron can gain sufficient energy from a photon to move to higher energy shell farther from the nucleus, or it can lose energy by emitting a photon and jump to a lower energy shell if it is not fully filled. Electrons in the outermost shell or orbit are called valence electrons. Valence electrons determine the chemical properties of an element since they are lost, gained, or shared between atoms in a chemical reaction, forming various chemical bonds like ionic bonds, covalent bonds, hydrogen bonds, metallic bonds, etc. An atom with completely filled valence electrons is stable and does not gain, lose or share electrons with other atoms, so it is chemically inert or non-reactive. Atoms with one or two valence electrons are very reactive since they can readily lose the valence electrons with low energy and form positive ions. Atoms with one or two valence electrons less than what is required for a fully filled shell are very reactive, since they can readily gain the electrons and form negative ions. Atoms can share valence electrons and form covalent bonds. Hydrogen H, helium He, and lithium Li follow duet or duplet rule, according to which having two valence electrons leads to stability. Helium has two valence electrons and is very stable. Hydrogen has one valence electron and it needs to gain one electron to attain the 1s2 stable structure, and lithium needs to lose one electron to attain the 1s2 stable structure. Octet rule applies to p-block elements, which tend to bond in such a way that each atom has 8 valence electrons in its outermost shell for stable structure. D-block elements tend to obey 18 electron rule with full valence configuration D10, S2, P6. Calcium, Ca, atomic number 20, has electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s is the outermost shell, so it has 2 valence electrons. Elements are arranged in a periodic table according to their properties, in various rows or periods, 1 to 7, and columns or groups, group 1 to group 18, lanthanides, actinides, and blocks S, P, D and F after its characteristic orbital. These elements can be classified as alkali metals, alkaline earth metals, transition metals, other metals, metalloids, nonmetals, halogens, noble gases, lanthanides, and actinides as shown below. Each row or period represents an electron shell. Elements in the same group tend to show similar chemical characteristics. Metallic character increases from top to bottom in a group and right to left in a period. Non-metallic character increases from bottom to top in a group and left to right in a period. Group 1 elements are called alkali metals and are very reactive, as they have one valence electron and can easily lose this to attain a stable structure. Group 2 elements are called alkaline earth metals and are very reactive, as they have 2 valence electrons and can easily lose these to attain a stable structure. Group 1, Group 2 elements and helium are the S-block elements. Group 3 to Group 12 are transition metals and D-block elements. Elements from atomic number 57 to 71 are lanthanides, and from 89 to 103 are actinides. Lanthanides and actinides are F-block elements. Group 13 elements have 3 valence electrons. Group 14 elements have 4 valence electrons. Group 15 elements have 5 valence electrons. Group 16 elements have 6 valence electrons. Group 13, 14, 15, 16 elements are all p-block elements, which can be either non-metals, metalloids or other metals. Group 17 elements are halogens. They are highly reactive as they are 1 electron short for completely filled valence shells. They have 7 valence electrons. Group 18 elements are called noble or inert gases, as they do not react because of their completely filled valence shells. Except for helium, which has 2 valence electrons and is a s-block element, all noble gases have 8 valence electrons and are p-block elements.